seminars is already lucky number 13. Cannot believe that we have been able to run it continuously for that. I would like to emphasize again that this WEM seminar will be live, which I will make it live right now. So please go ahead and go to WEM Facebook page and share the event so that the exchange of knowledge can reach to a wider audience within your network. Thank you. Okay, so it is already live. Thank you, everyone. Okay, so please give me a moment. Okay, let me share my screen. First, I would like to introduce our first presenter today, Mr. 𝐶𝐬𝐬𝐬𝐞. So he is no stranger to our WEM here, but I will take the liberty to introduce him to all of the students. And also we have some prospective students that have been in touch with me and some other faculty to explore the opportunities at WEM. So Mr. 𝐶𝐬𝐬𝐬𝐞 is currently a PhD student under Professor Babel. His research interest, let me zoom in a little bit. His research interest includes water resources modeling, water security, water energy food nexus, climate change impact assessment. Coming to our WEM seminar series today, Mr. 𝐶𝐬𝐬𝐬𝐞 will be sharing with us his research topic on assessment of water security river basins of Thailand. And the second one, let me stop share and next, our second presenter will be Ms. Usha Ghimai. So Ms. Usha Ghimai is also a WEM graduate, and her research interest, her core research interest includes climate change, land use analysis, hydrological modeling, and GIS. Coming to our WEM seminar series today, Ms. Usha will be sharing with us her research on climate change and land use change impacts on spatial temporal variations in groundwater recharge, a case study of the Bangkok area, Thailand. So we have quite very nicely balanced of topics today, covering from natural basins for the first presenter, and second, we will square down to a more localized, urbanized context with the second presenter. So with that, I would not take any further delay and would like to invite Mr. 𝐶𝐬𝐬𝐬𝐞 to start sharing the screen so that our seminar can start today. Please, the floor is yours, Mr. 𝐶𝐬𝐬𝐬𝐞.
Okay, thank you, Dr. Locke. Can you see my screen?
Yes, your screen is visible.
Okay.
You might want to use the pointer option when you do the presentation. Thank you.
Yes. So it's okay now, right?
Yes. Thank you.
So thank you, Dr. Locke, for that introduction. First of all, I would like to give a warm good morning, good afternoon, and good evening to everyone who are attending this seminar from different parts of the world. I would like to thank the Water Engineering and Management program at AIT for providing me this opportunity to present my research. I'm 𝐶𝐬𝐬𝐬𝐞. I'm a PhD candidate at the WEM program. So I will be talking about a part of my research titled Assessment of Water Security in River Basins of Thailand. So the content of my presentation today consists of a research background where I'll be talking a little bit about the what, why, and how aspect of water security, followed by the objective and scope, the study area and data, and the methodology used, and result and discussion, and finally some conclusion on the study. So let me begin with this figure, which highlights that water crisis has been listed as one of the top 5 global risks in terms of societal impacts over the past few years. And if we look into water stress, then we can see that almost about 2.3 billion people live in water stress countries, and most of and this figure shows here that most of them living at extremely high stress is in Asia. And water scarcity has already affected 4 out of every 10 people. And looking into the global water demand, it has been projected to increase by about 20 to 30% by 2050. And if we look at this highlighted figure here, it shows that the industrial water demand will increase by 8 times in African countries, and while it will increase by 2.5 times in Asia. Likewise, if we look at extreme events and disasters, then we can see from this figure that the trend of climate and weather related disasters have significantly increased over the decades in comparison to other kind of disaster. So this includes water related disasters such as flood, storm, and droughts. Furthermore, looking into the water pollution, we can see that the global issue shows that almost 80% of all industrial and municipal wastewater is released into environment without any prior treatment. So the figure here also shows the situation is very concerning in terms of proportion of household wastewater safely treated, and more than 80% of wetlands are also have estimated to be lost since the pre-industrial area. And so addressing these challenges is even more difficult, with climate change having placing additional stress on water resources and making water security even difficult to achieve. So ensuring water security is an urgent challenge, because it could threaten the lives and livelihood of billions of people if it's not addressed. So achieving water security is therefore a global concern. But what actually is water security? How is it defined? So different disciplines have different perspective of the term water security. So if we look at agriculture discipline, then they would define water security as the amount of water available for agricultural production and for food security. Likewise, water resource discipline would mostly focus on water scarcity and supply and demand security. Environment science would be more in concern with water services for human and the environment. And from the policy discipline would look more from the aspect of sustainable development and protection against water related hazard, and so on. But a more holistic definition of water security is given by the UN Water 2013, which is also widely accepted concept. And that defines water security as the capacity of people to safeguard sustainable access to adequate quantities and acceptable quality of water for livelihood and socioeconomic development, along with ensuring protection against waterborne pollution, water-related disaster, and for preserving the ecosystem. So with that definition in mind, water security is central to all form of security. So if we ensure water security, then we will also be ensuring food security, energy security, and climate security, and so on. But the first step to improving or enhancing water security is to measure it. So as there is an adage that goes, you cannot manage what you cannot measure. So if we look into different literature, there has been several attempts in measuring water security. So for example, Gain et al. At 2016 have taken different elements of water security to assess at the global scale. And so on, there are several studies that has been carried out at urban scale, at national scale, basin scale, and has been applied in different parts of the world. However, by looking into these studies, it was observed that most of the studies were carried out at national or urban level. And while it's good to have a assessment carried out at national scale, it can also, there is a risk that it can mask the significant variation in water security at local scale. So the situation might be completely different at local level than what is there at the national scale. And likewise, if we look at the local or city scale, which are emphasized for operationalizing water security, because it usually enhancing water security will require bottom up approach for this kind of assessment. They are unable to capture the linkage of hydrological characteristics of the watershed in which the city resides in. So this study is carried out to seek and address this knowledge gap by developing a framework for water security assessment at basin scale from the perspective of hydrological boundaries, and assess all the water security situation in 25 river basins of Thailand, with a view to assist in formulating and monitoring the strategies, plans, policies for water resource management at national scale. So the objective of the study is to develop a water security framework at basin scale and assess the water security condition for all river basins of Thailand. The scope of the study was indicator-based approach has been used for developing the framework. There are 5 dimension, 11 indicators for assessing the water security, for which we will go into detail. The normalization for the variables to bring them to a score of 1 to 5 has been carried out using different reference values from literature. And then equal weightage has been provided to variable indicators and dimensions for aggregation purpose. So moving on to the study area and data, the study area for the for this study is the 25 river basins of Thailand, which has been presented in this figure here, and their characteristics are tabulated here, which I will not be going into detail due to time constraint. And moving on to the data, most of the data that has been used for for measuring water security are secondary data source, which has been collected. For example, demographic data have been collected from the National Statistical Office of Thailand and the National Economic and Social Development Board. Similarly, meteorological data are collected from the Thai Meteorological Department, Rural Irrigation Department. Water use data are collected from the Metropolitan Waterworks Authority, Provincial Waterworks Authority. Area-related data are collected from the Land Development Department and other respective departments. Water-related disaster data are collected from the Department of Disaster Prevention and Mitigation. Water quality data are collected from the Pollution Control Department. And moving on to the methodology, in order to develop the framework, first literature review was carried out regarding the water security concept and defining water security, what are the methods that are there, and different indicators and SMART criteria. And based on this, the framework was developed by selecting the dimensions, indicators, and variable appropriate for the basin scale and defining them, and normalize how to normalize these variables were discussed and confirmed, and then weightage and aggregation method, which would give to the water security index, and what is its interpretation of the water security index. And finally, it was applied at all river basins of Thailand by collecting the data and normalizing these variables and providing equal weightage to the variable indicators and dimension, and then aggregating them to obtain the overall water security index. So at the figure at the right shows the structure of the framework. So we have the water security index, which is an aggregation of these 5 dimensions of water availability, productivity, disaster, health, and governance. And these are measured through 11 indicators listed here. And these indicators are quantified using different variables. So these variables can be selected by user based on the data availability and so on. So I would like to mention that the framework is at dimension and indicator level is kept fixed, so that the framework is generic and it can be comparable between if we apply it for different basins all over the world. So that will help to make it comparable among these different basins at different regions. Whereas the variables are kept flexible in the sense that these variables will be chosen based on the site-specific nuances or characteristics of the basin, and that can reflect upon these indicators. So in that way, we are providing a generic as well as site-specific aspect of the basin. So looking into the details of the framework developed, so I will not go into all of these dimensions and detail behind it, but however, let's look at one of them, one of the dimension of water productivity, which is measured through the indicator economic value of water. So this has been quantified using two variables of commercial industrial revenue per unit of water and agricultural aquaculture and livestock revenue per unit of water, and its estimation process has been listed here in table. Similarly, water related disaster is measured through two indicators, drought factor and flood factor. The drought factor is quantified through the variable drought damage, whereas the flood factor is quantified through flood damage. And if we look at the water governance dimension, the variables are quantified, measured through the questionnaire survey that was carried out in all of these 25 river basins. So the detail we will also go in it. So the framework that we have developed is also linked to the 2030 development agenda, which is the sustainable development goal. So the framework is able to reflect or address the SDG 6 targets and SDG 11, one of the target. So if we look into each of these dimensions, the water availability is able to reflect or address the 6.1 target of safe drinking water for all. Similarly, water productivity is able to address the 6.4 SDG targets. Water related disaster is able to reflect on the target of 11.5, which is to reduce the adverse effect of natural related disaster. Likewise, watershed health will be able to address the 6.2, 6.3 and 6.6 targets. Water governance would also help to address the target of 6.A, 6.B and 6.5. So the table here presents how the variables are normalized for these different for these selected variables for quantifying the indicators. So let me take an example of per capita water availability variable. So if the per capita water availability for the basin is in the range of 500 to less than 800, then it will receive a score of 1. Whereas if the per capita water availability is greater than or equal to 1700, then it will receive a score of 5. And all of these reference values are taken from some reference literature that has been highly recognized, and accordingly this has been categorized. So calculating the water security index is quite easy, because what we do is first the variable are normalized between 1 and 5, and then they are aggregated and averaged to get an indicator score. Likewise, these indicator score are then aggregated to give dimension score, which are then the dimensions are aggregated and averaged to give the water security index. So this is exactly the same formula behind the concept. So moving on to the result and discussion part. So let me present the result from the first dimension, water availability dimension. So if we look at the trend from 2007 to 2015, we can see that almost all of the basin of Thailand performs very well from this dimension, because they have the water availability score range in the very good to excellent range. So this dimension is quite from this dimension perspective, the almost all of the basins are quite the situation is quite favorable for these basins. And looking into the water productivity dimension, so if we look from 2007 and compare it with 2015, we can see that the situation has somewhat improved for most of the river basins. However, since this is an aggregation of both the agricultural productivity and commercial water productivity, the agricultural productivity is still a cause of concern in this river basin, most of the river basin. However, the overall water productivity is counterbalanced by the massive improvement in industrial or commercial water productivity. Likewise, if we look into the water-related disaster dimension, then we can see that this dimension was a major cause of concern from 2007 till 2011. We can see that most of the river basins at northern part and northeast part are very vulnerable and have poor water security, poor water-related disaster from 2007 till 2011. However, from 2012 onward, and if we look at 2015, we can see that the situation has significantly improved for most of these basins, where we can see that even at the northeast part and the central part, the situation is somewhat good. So this significant improvement has occurred over the time period in terms of water-related disaster, maybe because some intervention might have been taken after the flood, major Thailand flood of 2011. Likewise, if we look into the watershed health dimension, we can see that overall the water security, watershed health, it ranges, the score ranges from very good to very good for most of this river basin, and somewhat the situation is still favorable in terms of overall watershed health dimension. However, if we look from the indicator perspective, then health of water bodies and proportion of wastewater safely treated is still concerning areas for most of these river basins. Likewise, finally, moving into the water governance dimension, it has been measured through questionnaire survey that was carried out, and the questionnaire are presented here for the variable of institutional factor and adaptability factor. So these questions were asked for all the river basin committee members for all the river basins, and the answer responses were categorized into 5 categories. And based on the questionnaire survey that was carried out, the graph here shows the number of committee members and the responses that we received for each of these basin, and the total committee members in all of the river basins are 761, and we have received almost about 31% of responses from all the river basin committee members for all the 25 river basins. So an example is presented here for one of the question where it was asked with the river committee members that does the basin have integrated water resource management plan? And if we look for one of the basin, 𝐶 River Basin, then we can see that almost 25% has said that it has been partially implemented in 𝐶 River Basin, while almost 63% says that it has not yet been implemented, although the plan is there, but it has not been implemented, and about 13% says that it's still under consideration. And based on these responses that we received and looking into the overall water governance index, we found that while the basins have reasonable water governance, there are hardly any basins that have excellent to very good water governance. So looking into the overall water security index, which is an aggregation of all those dimensions, then we can see that from 2007 to 2015, water security has improved for most of the river basin, and the main improvement has been mainly with the improvement in the water related disaster dimension. And however, the watershed health dimension has degraded in several basins, and overall the water security condition in most of the basin is in the range of very good for 2015. So from the conclusion of the study, we found out that the overall water security in Thai River Basin is quite satisfactory. However, individual dimensions, there are some concern in regard to individual dimension. For example, the watershed health is an area of concern. So the concerned authority really need to step up some effort to enhance the wastewater treatment capacity in order to improve the health of river basin. Likewise, from the perspective of water productivity and water governance, basins also need to improve in these dimensions, where the concerned authority could emphasize on capacity building for farmer to enhance their agricultural productivity and enhance proper water resource management plan and adaptation for future water challenges to improve on their water governance dimension. There's still some research that is required to arrive at some intervention on how we can actually improve the water security based on the framework that is developed. Overall, the framework will be useful to determine the Thailand's progress made on SDGs. So thank you very much for your patience and listening to my presentation. I would welcome any questions. If you have any, please let me know. Thank you.
Okay, thank you, Mr. 𝐿 for presenting a very informative presentations. Actually, I was mostly amazed by the amount of information, considering the punctuality of your presentation, which is very much appreciated. We have some first comers to our WEM seminar, so I would like to take a couple of minutes to introduce to them that this WEM seminar is organized either bi-weekly or monthly, depending on our semester timing. So at this particular period of time, it's a monthly event. But usually it is a bi-weekly. So each of the seminar will have two presenters. We initiate this WEM seminar as kind of a knowledge exchange platform for our WEM graduates, alumni, and also a connection opportunities to our WEM family through our alumni and also prospective students. We have some prospective students over here. So when you can come and join our family, this would be a very meaningful extra curriculum that you are very encouraged to join. With that, I would like to open the floors for questions and comments to Mr. 𝐿. For those of you who want to ask questions directly, please unmute yourself. If possible, turn on your video as well and ask questions directly to the presenter. Thank you. Okay. Any questions for Mr. 𝐿? I think this is a very informative and meaningful, especially when you make use of the big data and tie that very nicely to the SDGs goals. Any questions? May I invite Saurabh as well? I think Saurabh also working in the topic of indicators. Maybe you have some comments for your friend.
Thank you, Dr. Lal. A nice presentation, Kaushal. Actually, Kaushal and me, we are sharing the same office room. So we have been discussing on this work from quite a long time. But still, I haven't seen the full comprehensive work. I don't have actually the question, but maybe some confusion if you can clarify for me. Since I'm looking on the governance aspect, as Kaushal have also helped me in many aspects on that. So I just want to know, like this governance questions or this qualitative questions that you have conducted for the governance assessment, does that address the all these 12 dimensions of water governance, or it's just like outline? First, my one question is that, and one I just want to like know from Kaushal's view on that. Since in the research question you said that institutional demand, or sorry, this industrial demand will be one of the major demand in the future. So how will your framework address this demand when we do a dimensional analysis or indicator-based analysis? So how many indicators are there, or how can this be modified so that later if some basin or some country want to check for their institutional capability or security from security point of view, so how will it address? Only these two queries, if also could answer, then it would be great.
Thank you, Saurabh, for your questions. Please.
Thank you, Saurabh, for that question. Let me first go to your first question of whether of this questionnaire. So actually, as you're well aware that and you're working on the water governance aspect, so you definitely know that it has a wide range of spectrum. So we are from this framework, we are only looking into basically two spectrum of institutional factor, and whether if the basins are capable to adapt to future changes. So we are only concerned with those, because our point of view is that the framework should be operational, so that it's operationalized. So if we list out all the aspect or spectrum of water governance, then it itself is another framework, or it itself is very there is a complexity within it itself. So these questions are only will only reflect on the institutional and adaptability factors, not on the all dimensions. So from these questions, we have carried out this questionnaire with all the river basin participant by by conducting assessment at with governmental officials, as well as different water groups and farmers, even through phone interviews and so on. So these are mostly reflecting on the institutional factor and the adaptability factor based on their responses. So that's how we have evaluated the water governance dimension. And regarding your second question of industrial demand, which has been projected to increase in 2050. So we have this one of this dimension of water productivity, where we are looking into commercial industrial revenue per unit of water. So based on this variable, or based on the indicator of economic value of water, we will also be able to identify like what is the status, whether if what is the level of water consumption in these industries. For example, in our case for Thailand, let me show you from the perspective of commercial and industrial revenue per unit of water. So you can see that Thailand water consumption is relatively low in terms of the revenue it generates. So which is why the commercial and industrial revenue per unit of water is quite secure from the productivity aspect. But however, if you look at agricultural water productivity, you can see that the revenue generated is very low in comparison to the water consumed. So, and you can see that the situation has deteriorated over the year. So that can provide you an insight that, okay, so how the water demand, or how the water consumption needs to be improved, or it needs to be addressed, so that how the basin should focus on some measures or interventions on how they can reduce this water consumption. So that kind of insight will be able to be we can be able to present based on our framework. So I hope that answers your question.
Yeah, Kaushal, yeah, thank you so much.
Yeah, thank you, Saurav. That is a very high level, knowledge exchange between our two students. I want to just take very short time asking Kaushal on 2 points to add on what Saurav said. Also related to the point of consumption. So what you're implying is because there are a lot of farmers, and then using water for farming does not generate too much revenue. I think it's a little bit of a, I would say conservative way of putting it, because Thailand is an agricultural country, right? Not yet an industrial. So that's why more water should be diverted to that. And also, you have to consider also the food security and social equity perspective as well. It's not a very straightforward dimension that, okay, industry can generate more money, so we should put more water to industry sectors. In fact, actually, the industry factor should pay more so that we can compensate the use of agriculture, right? And I think that's the practice in developed countries. Of course, not the case here, but that's something for you to explore. The second thing is a small question. Have you done, can you come to the slide where you did a questionnaire across the catchment, the questionnaires of the catchment? Yes, this one. So it seems like, no, the statistics of the catchment managers. Yes, this one, yes. So No, 37, yes, this one. So my very quick question is, it seems like there is a large diversity of the implementation of IWRM across the basins. So have you found any statistic correlation between the implementation of IWRM with the water governance or the water health of the basins or not? So the hypothesis I would like to check is that will the implementation of IWRM can increase the water security or water productivity or water governance or not? Have you done any correlation yet?
Thank you, Dr. Locke, for your wonderful questions. Let me first talk about the first aspect that you raised. Well, I completely agree with you with your statement that looking only into the consumption and looking only into this single variable and telling that, okay, water needs to be conserved is quite difficult. I mean, it's not that directly, there's a lot of complexity involved as well, but we were focused more from the operational point of view. So we have only selected, if you look at the framework, we have only selected one indicators or two indicators for almost all of the one or two variables for all of these indicators to quantify them. However, we have a list of variables, so so the selection of variables to quantify the indicator is equally important for indicator based approach. If we because by selecting a different variable, I could have a different outcome generated. So which is a kind of a very important discussion that I want to also highlight here, because by selecting selection of these indicators, variables should come with stakeholder discussion. So it should not be simply by doing by simply looking into literature and adapting them, but should come up from the concerned authorities and different stakeholder involved. So that would make the framework really robust. So that is one of the aspects that I want to highlight here. And regarding your second question of statistical correlation among IWRM, I think that is a really good hypothesis that if we test, I think it could bring out interesting result. However, for this study, because the quantum of the work was quite heavy, so we were more concerned with only evaluating the state of water security. So because since there was no any evaluation or disaggregated assessment that was carried out at basin scale for all the river basins in a country, so we were more interested and more focused on that. So maybe this could be one of the future research that we can take up and evaluate this hypothesis that you have mentioned.
Okay, thanks, Kaushal. I think it would be interesting if we can recheck our claim that right, because we've been talking about IWRM, and this is a beautiful opportunity where we really can verify the hypothesis on the ground. So thank you, Kaushal, for your wonderful presentation. So before we move on to the second presenter, as may I? Okay, thank you, Kaushal. So may I invite our photographer, Mr. Roel, to coordinate the group photos. So just for all of you who have come the first time, we have this tradition that we always have the group photos of a WEM seminar. So if possible, I would invite all of you to turn on your camera so that, and then follow our photographer, Mr. Roel, over here to take a group photo. Thank you, everyone. Mr. Roel, on your mic. Thank you.
Okay, good morning to everyone. So please turn on your camera. So wait for a while. Okay, prepare. So in count of 3, 1, 2, 3. Okay, one more. 1, 2, 3. Okay, thank you very much for everyone.
Brilliant, Mr. Roel, for being a very reliable photographer as always. we're really looking forward to have this physical again in the very near future. So with that, I would like to invite our second presenter, Ms. Usha Kimaya, for sharing. You can start sharing the screen and start your presentation. Thank you. The floor is yours.
Yes, thank you so much, Dr. Luck. Can you see my slide?
Yes, your slide is visible now for full screen. You may start. Thank you.
Yeah, thank you, sir. Good morning, everyone. First of all, I'd like to welcome you all in the WEM seminar on climate change and land use change impact on spatiotemporal variation in groundwater recharge, a case study of Bangkok area, Thailand. I am Usha 𝐬𝐻𝐬𝐬𝐬𝐬𝐻𝐬, a research associate in water engineering and management program at AIT Thailand. In this presentation, I'm covering the following part, that is introduction, materials and method, result and discussion, conclusion and recommendations. Let me begin with the background of the story. The demand of water has been increasing over the past decades because of the population growth, rapid economic development, and changing consumption pattern globally. In Thailand also, more than 35 million people living in rural and urban areas are depending upon groundwater resources. Climate change is globally acknowledged as one of the most significant challenges causing disturbance in humanity. The excess groundwater abstraction lead to numerous challenges such as groundwater pollution, health hazards, loss of properties, flooding, and devastation of infrastructure facilities. Moving into the statement of problem, Bangkok city is occupied by more than 13% of the whole country's population and is core for the most of the economic and commercial activities. Due to the large scale of groundwater use in the study area, there has been an adverse economic and environmental problem like continuous reduction of potentiometric level in pump aquifer, water quality degradation by saltwater intrusion, and land subsidence. Climate change might add immense pressure on groundwater by affecting the groundwater recharge rate and changing the availability of groundwater. Therefore, this story relating to the impact of land use change and climate change on groundwater recharge is imperative for bridging the research gap. The objective of the story focuses on the impact of climate change and land use change on groundwater recharge, and specific objectives are to analyze the future climate change using the quantum mapping technique, to investigate the past, present, and future land use pattern employing the dynamic model, and to estimate the spatial and temporal groundwater recharge distribution in Bangkok and its vicinity using the hydrological model Watershed. Now moving into the study area. The study area mainly consists of Bangkok and its surrounding province, that is Pathum Thani, Samut Prakon, Samut Sakon, Nakhon Phatom, and Phra Nakhon Ayutthaya, with a total catchment of 10,300 square kilometer and total population of 11.3 million according to the census 2010. The average precipitation, the average high temperature, and the average low temperature were found to be 1,146 millimeter per year, 33.12 degrees Celsius per year, and 23.50 degrees Celsius per year. The seasons are mainly divided into wet season and dry season. Wet season consists of May, June, July, August, September, and October, and dry season consists of January, February, March, April, November, and December. The study area is located in the tropical region. Figure shows the location map of Bangkok and its vicinity with the all meteorological station and river network. Moving into the data and source required for this research, the topography of resolution 90 meter by 90 meter was obtained from United States Geological Survey website. The land use map of resolution 300 meter by 300 meter was obtained from European Space Agency website. Soil map was obtained from Food and Agriculture Organization of United Nations website. The meteorological data from year 1976 to 2005 was obtained from Thai Meteorological Department, TMD, Thailand. The population density per square kilometer and road network of resolution 300 meter by 300 meter was obtained from GIS. The groundwater level data was obtained from Department of Groundwater Resources, Thailand, and the river discharge data was obtained from Royal Irrigation Department, Thailand. These are the meteorological data that we use for this research. The name and location of the rainfall and temperature station used for this study was obtained from the Thai Meteorological Department. Similarly, the figure on the right-hand side shows the location map of meteorological data in Bangkok and its vicinity. The geospatial data that we use for the dynamic model for the land use projection by dynamic model is shown in this slide. The figure shows the digital elevation model, aspect ratio, slope, population density per square kilometer, Euclidean distance from road, Euclidean distance from river, soil type map of Bangkok and its vicinity, Thailand. The conversion sequence and conversion elasticity for dynamic model is shown in the following table. Table on the right-hand side shows the conversion elasticity used for dynamic model in Bangkok and its vicinity, and the table on left-hand side shows the conversion sequence used for dynamic model in Bangkok and its vicinity, Thailand. The overall methodological framework is shown in this slide, and the methodology is further divided into 3 objectives. For the first objective, to project the future climate scenario, 3 regional climate model, SS, MPI, and CNRM for RCP 4.5 and for RCP 8.5 was used. To remove the biasness from future climate data, quantum mapping was used. Also, R-squared, RMSE, and standard deviation was done to check the accuracy from the future climate data. To project the land use change scenarios, a dynamic model was used for the model setup. Baseline land use map along with all the geospatial data were input into the model. The model was then calibrated by comparing baseline land use map with the simulated land use map. The 3 land use change scenarios, that is high urbanization, medium urbanization, and low urbanization scenarios, were input into the calibrated dynamic model to obtain future land use change scenarios. And similarly, for the similarly for the future groundwater recharge under climate change and land use change scenario, we use hydrological model which is passed. For model setup, the spatial data, hydrometeorological data, and DVF files were used. After that, the model is then calibrated to evaluate the effect of climate change and land use change on groundwater recharge. For groundwater change, land use change scenarios, 3 land use changes were created. For high urbanization scenario or business as usual scenario, future land demand was assumed to follow the historical trend. Medium urbanization scenario, the best of areas were assumed to increase up to 25% of total land area by 2099, followed by small decrease in agricultural land, forest, and grassland. And for low urbanization scenario or conservation scenario, the forest was assumed to increase up to 25% of the total land area by 2099, followed by small decrease in agricultural land and grassland. Now moving into the result and discussion section, projection of future climate. The average annual baseline precipitation of Bangkok and its vicinity was found to be 1,146 mm per year. The precipitation is not uniform and is varying throughout the future. For RCP 4.5 scenario, MPI projects the increase in future precipitation by 20.6 mm, 59.7 mm, and 82.6 mm for near, mid, and far future. Similarly, for RCP 8.5, the increase in maximum precipitation was found to be 168.9 mm for far future, and the decrease in maximum precipitation was found to be 115.7 mm in near future. Now moving into the seasonal analysis of the future precipitation. For dry season, all RCMs and both RCP scenario projects that the increase in future precipitation is there is increase in future precipitation. The increase in future precipitation ranges from 16.6 millimeter to 73.8 millimeter in case of RCP 4.5. For RCP 8.5 scenario, the increase in future precipitation ranges from 9.9 millimeter to 145.1 millimeter. For wet season analysis, ICS RCM is projecting the maximum increase in future precipitation by 98.7 millimeter and 98.4 millimeter in far future for RCP 4.5 scenarios and RCP 8.5 scenarios respectively. CNRM RCM projects the maximum decrease in future wet season precipitation by 115.5 millimeter and 132.2 millimeter in near future for RCP 4.5 and RCP 8.5 scenarios respectively. Now moving into the analysis of future maximum temperature. All RCMs and both RCP scenario agrees that the maximum temperature will increase in future. The increase in maximum temperature ranges from 0.6 to 1.4 degrees Celsius for RCP 4.5, and the increase in maximum temperature ranges from 0.6 degrees Celsius to 2.5 degrees Celsius for RCP 8.5. For analysis of future minimum temperature, for RCP 4.5 scenario, the increase in future minimum temperature ranges from 0.7 degree to 2.1 degree Celsius, and for RCP 8.5, the increase in future minimum temperature ranges from 0.1 degree Celsius to 3.8 degrees Celsius. Performance of bias corrected precipitation and temperature. R-square for the precipitation ranges from 0.104 to 0.422. R-square for maximum temperature ranges from 0.124 to 0.682. R-square for minimum temperature ranges from 0.611 to 0.792. R-square for bias corrected RCM data is always higher than raw RCM data, and RMSE for bias corrected RCM data is always less than raw RCM data. Now, projection of future land change. For this, at first we analyze the past land use. The bar graph shows that the area covered by agricultural land goes on decreasing, whereas the area covered by built-up goes on increasing from year 2008 to 2015. Spatially, we can see that the observed land use map in 2008, 2010, 2012, and 2014 in Bangkok and its vicinity, Thailand. The validation of the 𝐸 model was done by using kappa index. The table shows the area of land use class for observed period 2015 and simulated period 2015. The table shows that the observed land use map perfectly match with the simulated land use map. The kappa value was found to be 0.81. Figure on right hand side shows the comparison of the observed land use map of 2015 with simulated land use map of 2015 by the land use change by the 𝐸 model. Now, projection of future land use change for high urbanization scenario. In this, the table shows that area and percentage of land use classes for different years for this study area. The area covered by agricultural land goes on decreasing from 69% in 2015 to 33.05% in 2095, whereas the area covered by built-up goes on increasing from 15.36% in 2015 to 52.2% in 2095. Partially, we can see that the area covered by built-up goes on increasing as we move to the future map. For medium urbanization scenario, the area covered by agricultural land goes on decreasing from 69% in 2015 to 62.42% in 2095, whereas the area covered by built-up goes on increasing from 15.36% in 2015 to 24.49% in 2095. Especially, we can also it is clear that the area covered by agriculture is decreasing in less amount. In the low urbanization scenario, the conservation of forest is given priority. So the area occupied by forest goes on increasing from 6.98% from 2015 to 24.10% in 2095. Now moving into the result for hydrological modeling, water balance of Watershed model. The table shows water balance of Bangkok and its vicinity obtained from Watershed model. Annually, the water balance from inflow in forms of precipitation was found to be 1,146.5 millimeter, and outflow in form of recharge, actually evapotranspiration and surface runoff were found to be 115.3 millimeter, 625.8 millimeter, and 405.4 millimeter, respectively. Estimation of groundwater recharge under all urbanization scenarios. Now, moving into the estimation of groundwater recharge for high urbanization scenario and medium urbanization scenario. For both RCP scenario, the graph shows that groundwater recharge is projected to decrease. For high urbanization scenarios, the decrease in groundwater recharge is higher for RCP 4.5 scenario, and decrease in groundwater recharge for wet season is more significant. Similarly, for low urbanization scenario, there is an increase in groundwater recharge for annually dry and for wet season, respectively. Now, the estimation of groundwater recharge under all urbanization scenario and climate change scenario. This table shows that the summary of change in annual dry and wet season groundwater recharge under RCP 4.5 and RCP 8.5 scenario during 3 future periods, 2030, 2060, and 2090, relative to the baseline period 2001 in different land use change scenario for Bangkok and its vicinity, Thailand. Now, moving into the conclusion obtained from this research, we can draw the following conclusion. The future precipitation is not uniform and varying throughout the future. The annual average future precipitation in dry season is projected to increase under both RCP scenario, whereas the annual average precipitation in wet season is projected to decrease in near and mid future and increase in far future, for both RCP scenarios. Temperature is projected to increase in Bangkok and its vicinity, Thailand during all future time period in both RCP scenario. The increase in minimum temperature is higher than increase in maximum temperature. 3 land use change scenarios were developed in order to analyze its impact on groundwater, and they are high urbanization, medium urbanization, and low urbanization scenario. Similarly, future groundwater recharge is projected to increase in low urbanization scenario, and both RCP scenario, the groundwater recharge is projected to decrease in future for high and medium urbanization scenarios, and both RCP scenarios. The decrease in future groundwater recharge is significant in wet season. Recommendation from this research: based on the result of this study conducted, we can recommend the following points. The precipitation pattern is expected to fluctuate seasonally, causing seasonal imbalance in water. Therefore, different structural and non-structural measures be implemented for effective management of water resources. Another point, land use change by increasing built-up area has caused past impact on groundwater recharge. So urban planning must be done properly in order to manage the haphazard increase in built-up area in Bangkok and its vicinity. This research has already been published, and you can go through this link and download the research. Thank you so much for your attention. If you have any question, you can ask me freely.
Thank you, Ms. Usha, for, I would say, very interesting and then informative presentation. So with that, I would like to open, yes, thank you. I would like to open the floors for some questions and comments for Ms. Usha. Anyone, if you have questions, please unmute yourself, turn on the video and ask questions directly. Thank you. Questions for Ms. Usha? Okay, I think looking in the topic of groundwater, we have quite a number of students. Please
Yes, sir.
don't worry. Yeah, so please don't worry. So please don't hesitate. May I invite Ms. 𝐶𝐚𝐬𝐬𝐿? As I recall, I think your topic was also related to climate change and groundwater. So maybe you can have some questions, comments for Ms. Usha. May I invite Ms. 𝐶𝐚𝐬𝐿?
Thank you, Dr. Locke.
Thank you.
Yes, thank you, Senior Usha, for your informative presentation. Actually, my thesis focus on influence of climate variable on groundwater storage as well. But I just would like to in my study, I analyze the significant, whether the changes is significant or not. But so I just would like to how to say it, give some recommendation if we can include to see if the impact of climate change or land use change is significant or not using the statistical indicator. Yes.
Hello?
Hello. Yes.
Yeah, you are talking about the using of indicator, something like that?
Yes, when your results show that the climate and land use change impact on groundwater recharge, but then we are not sure the changes is significant or not. So if we include use probability, a p-value or something to check if it is significant, the significance of the change.
Yeah, I think that that is also a good idea, but this is the part of my research. I have done other part also like groundwater modeling, but in this presentation, I have only mentioned up to groundwater recharge. And thank you for this suggestion. I will go through it.
Thank you.
Thank you, Ms. 𝐶𝐚𝐬𝐿, for your question. May I invite Mr. Muhammad? You raise your hand. You can unmute yourself and ask the question directly. Thank you.
Hello, assalamu alaikum.
Hello.
Hello.
Morning.
Good morning.
Good morning. But I don't know whether my question will be relevant to you since I came late. So
It's fine. Yeah, it's fine. It's fine. Just ask question directly. Thank you.
please, are you getting me?
Yes, sir.
Yes. Yes.
Okay. First, my question is, so regarding to the topic, discussion since, but I actually came late, but I don't know either my question will be relevant to the topic or I don't know even you have discussed it. So my question goes like this. One, so since I came from Africa, which is I'm from Nigeria right now, we have the contamination within the environment. Is that contamination will affect the groundwater? So based on our environment locality, we have a very much of contamination.
Okay.
So that contamination, will it affect the groundwater table? Then secondly, what are the actual pipe installment to reach the water table? So people are saying that when you are looking for the fresh water, groundwater is much more fresher than any other water, how many pipe will you install before getting the groundwater table? Thank you. That's all my question. I am Muhammad.
I got your question. Thank you for the question. But yeah, groundwater, comparing to the surface water and other spring water, the groundwater is less vulnerable to the direct contamination. But about the pipe you are talking about, the installation of pipe you are talking, it depends upon the groundwater table data that we need to analyze the groundwater level first, the depth of a groundwater level, and we can only install after that.
Mr. Muhammad, does it answer your question? No, Mr. Muhammad? Okay, I think we will wait for him later. While waiting, I just have one small comment to Ms. Usha.
Yes,
hello, Mr. Muhammad. I found him again. Mr. Muhammad, are you there? Okay, maybe some technical issues. I just have one small comment from myself for Ms. Usha. Can you come to the slide where you have the changes of the land use? I think also related to the water bodies. I think that's what, yes. So one of those, I think this is just a small issues, but if you look at the water bodies, it stays unchanged. You see, it stays unchanged. Yeah. I think this is a technical issues. It's like, I think you include the seawater at the southernmost. So I think it takes up most of the water bodies in your study area. Am I right?
And actually, the study area, we try to make the water bodies constant throughout the future. So we evaluate only on the other land use classes.
Okay, no. But my question is like the water bodies you include in your map is the sea, right? I think it's the big part into the sea, right?
Yes, sir.
Okay,
seawater
okay. So that, I think that's the reason why it stays unchanged. But because if it's inland, what I think if it is inland water system, then I think it might not stay unchanged. So I think this is something in the scope that should be mentioned. Because with all of the land use change, I think the surface water bodies, especially the lakes and the ponds, will also be affected to some extent. So that's just my small comment to you. Thank you, Ms. Usha. So thank you, Ms. Usha. So before we wrap up this session, I'm very happy to see that we have quite a number of our successful alumni joining us here today. I would like to address one of them. May I invite Dr. Bikesh, who is actually even my senior in WEM. So Dr. Bikesh, maybe you can have a word to all of our young water engineers over here. May I invite Dr. Bikesh. Thank you.
Yeah. Okay.
Yes.
Welcome, yeah, hi everybody. Yeah, this is Bikesh. I'm in New Zealand currently. It's very nice to see this kind of thing being organized. I would like to congratulate both presenters. I really enjoyed the presentation. You guys are doing a good job. I have nothing to comment at the moment, but it's a good platform that you guys are using, especially in current situation in pandemic, where online platform is extensively used. In fact, in my case, I'm working from home because of the lockdown, and everything is being organized, is being carried out online. So I'm very happy. And in future, maybe I will also like to share some of my knowledge in this platform. Thank you very much for giving me this opportunity to say some of the few words. Thank you.
Yes, thank you very much. Yes, thank you, Dr. Bikesh. I think definitely we will reach out to our alumni to share the knowledge with our current students and also to myself as a faculty. I actually actually one batch after Dr. Vikesh exactly 10 years ago. So it was really touching and inspirational to see him over there. Getting back on the memories. I think this is a unique feature of WEM. Because we are water and water flows in circles, it comes back like myself, and also from abroad, like Dr. Vikesh also comes back. So I think that's the beauty of our water engineering program. So we're trying our best to keep it that way for many years to come. So with that, I would like to wrap up today's seminar. Big applause to our two presenters, and I will be welcoming you again in 1 month's time. Until then, please stay safe and healthy. Thank you, everyone.
Thank you.
Thank you.
Thank you, everyone. Have a nice day.
Thank you, Professor.